Welcome to the New York City Category Theory Seminar. This is the end of spring 2023. Arthur Parzygnat is coming back. He spoke to us before, and he's a former CUNY, but he's now in Boston, and he's going to talk on inferring this past and using category theory to find retrodiction. Did I pronounce that right?
That's correct.
Perfect.
All right, thank you so much, Nelson, for the invitation.
Please.
And also for the honor for giving the last talk. I didn't realize that that's the way it planned out, so it's very nice to do that. So I'm going to be talking about a paper that is actually probably going to be published this week in the journal Quantum, and the archive number is here if you want to check it out. It's a fairly mathematical paper, but the roots of the concept come from some questions some questions in fundamental quantum mechanics. And before I really get started on the quantum mechanics side, I kind of want to give a feel for why category theory sort of showed up in the concept of retrodiction in the first place by going back to classical systems, classical probability, and doing things fairly on a simple level. So definitely feel free to ask me questions at wherever you have questions in those parts. And in the quantum mechanics side, I'll try to be fairly brief because there's a lot of tools that are involved, like talking about algebras and complete positivity and things like that, which might not be familiar to everybody. So I will try to I'll try to hide a few things under the cover, but use category theory as a means to make connections, which I hope will be more familiar. So let me start off by just talking a little bit about stochastic maps, which sometimes you may also hear another name for them, which are called noisy channels. Maybe if you're, study some information theory, they might go under many different names. And the way that I'm going to think about these is, let's just think about a probability first. So if you give me a finite set X, just of some elements, so let me draw those elements here, but you should think of them as being distinct. They all look the same, but they're distinct elements. And a probability distribution on such a set you can visualize this as taking each element and then thinking of each element as a water droplet with some volume, and that volume is the probability of that element. And the sum of these probabilities is equal to 1. So it says the total volume of these water droplets when you combine them is 1 with respect to some units. So this is how I'm going to imagine what a probability space is. And I'm going to imagine that not only do I have probability spaces, but I might also consider maps from one finite set to another. And for me, I'm going to draw these maps as F, and I'm going to say a stochastic map, in this case from X to Y, assigns to each point X and X a probability distribution on Y. And I'm going to call that probability F subscript X, and it's a probability distribution on Y whose value on Y on the point Y is Fyx, kind of like a matrix. So I think of the stochastic map as encoding a bunch of numbers that are indexed by the domain set and the codomain set, and I think of it as a matrix. And because Fx is a probability on Y, it means that, this is a parenthetical remark, it means, for example, that the sum over all Y is always 1, and each of these numbers are always non-negative. So that's what a stochastic map is. It's a map from a probability space to another. It's a map from a set to another set, that doesn't associate to each element another element, but associates to each element a spread of elements, each with some weight. So I think of a stochastic map as sort of creating one of these probability distributions for each point in the domain. And what I'm going to think about is, so in technical words, so maybe I can say this now. So let me say finite sets as objects and morphism and stochastic maps as your morphisms together form a category, and let's just call that thin stock. And this category actually has a lot of structure. For example, it has a monoidal structure. You can take the product of two finite sets in the usual way, the Cartesian product, and you can take the product of probability distributions, and therefore you can take the product of morphisms, stochastic maps as well. So it gives you a monoidal category. And there's a terminal object, for example. The single element set can only have one probability distribution on it. So there's always a unique map into it. But there's no initial object, because from a single point, for example, you can create many probability distributions. So you only have this terminal object, but you do have a monoidal unit. The monoidal unit is the single element set. And so this forms a category. Now, in general, stochastic maps aren't always isomorphisms in your category. In general, if you have an isomorphism in this category, it's going to be a stochastic map whose probability distributions that you always get upon an input are Dirac deltas. So they correspond to functions, and they correspond to actually invertible functions. So let me say that first. So
the thin stock, does it forget into finite sets? It forgets into finite sets.
It doesn't forget into finite sets because not every, so let me make even this remark before what I was about to say. So finite sets you can think of it as a subcategory of thin stock, where x goes to x, and a function. So now this is a function.
X goes to x with the deltas in finite stock, up on top.
Yeah, so the objects are sets, so those you don't touch.
Okay.
The sets are the same. It's what do you do to a function? If you give me a function associates to each element some other element, how do I think of that as a stochastic map? Then the stochastic map is defined by fyx, is given by the delta function at your input. Maybe it's a little abusive notation. But so if you give me a function f, I can create a stochastic matrix out of it. Let me call it f tilde for just a moment, whose probability of y given x, that's one way to say this too, is the Dirac delta 1 when this is y f of x. 1 if y equals f of x, and 0 otherwise. So it's the probability distribution that gives you 1 at your image element, and it's 0 everywhere else. So you really think of stochastic maps as like spreading out functions.
That's right.
So you have this inclusion in this direction, but I can't think of a natural map going backwards right now.
Is Finstock monoidal closed?
What does monoidal closed mean?
Does it have does a tensor product have a right adjoint?
I don't know, I didn't think about that. I won't
If I understood it correctly, yes.
Yeah. I mean, I think these are good exercises to think about. But I'm not going to think about them off the top of my head.
It obeys Curry.
Are you sure?
Yeah. Absolutely. So,
Actually, I should pause for a second. Any other questions so far?
Another question you may not have thought about, is there a fibered structure, thin stock over thin set or something similar?
Yeah, I think I'm about to talk about what I'm
Okay,
doing.
great.
I think.
Mhm.
Right. So, okay, so one of the points I wanted to make was that isomorphisms in thin stock correspond to bijections coming from this inclusion structure.
We could say those are noiseless channels.
Yeah, exactly. Well, so not only are they noiseless channels, but they're also like reversible channels. Channels that you can go backwards to, because a noiseless channel could be something that's like, noiseless I would think of as a function.
Yeah, something that comes from the ejection.
Right. And then isomorphism is like, it's noiseless, but it's also everything is identifiably, like you can go, sometimes you can go backwards and undo everything that you did. Welcome. So isomorphisms in this category correspond to bijections, and that seems like a rather, to some degree, that seems a little unsatisfying. You might want to know, if I have a noisy channel, yes, I might not be able to find an inverse for it, but I might want to try to find some notion, maybe take some properties of what the inverse assignment satisfies, and see if I can construct a new object, a new map that goes backwards, that satisfies some of the similar properties that the inversion procedure satisfies, but is weaker than actual inversion. And this is what retrodiction is. So this is what I'm going to talk about.
Sorry, correspond to bijections?
Yeah, coming from this inclusion. I'm being a little bit vague
Okay,
here.
I see. Okay.
Yeah, this isn't the part that I want to make too precise yet. But yeah, keep asking me those questions, because sometimes, at some point I'll get a little bit more clear, hopefully. Right, so I guess the moral of the problem of this talk is, can we find a way to invert, quote unquote, noisy channels rather than channels that aren't really so noisy? And the question is really going, the point of this talk is going to be to identify what we mean by invert. Okay. So let's try to do this by recalling something from statistics in a slightly categorical language. So first, I just want to note that a stochastic map from a single element set to X for some finite set X is a probability distribution on X. Right? Because if I take a single element set, the definition of a stochastic map says to each element I give you a probability measure. There's only one element, so that is a probability measure. So then let's look at the, I always forget these names, left, right, slice, co-slice, comma, something. But let's look at the category of, please correct my notation so that I get the right one, but is it like this? Slice category of morphisms into sets. So I'll tell you what the objects are. Objects are sets together with a probability distribution. So a morphism to X
Oh, it's the other
Yeah, I
way.
think so.
It's the other way.
I just,
That's the costless, yeah.
does it go like, I don't even,
Slash under.
No, like you would put like the slash after.
No,
so I should have permuted this?
yes.
Different people have different things.
Oh, down?
No.
Coastline. Go in front of the F there.
I'll just draw an up arrow.
No, you go in front of the F. Okay? You go
Put
start.
the-
Yeah, like
Perfect,
that.
perfect.
Yeah, well, with a slice. There.
I don't know how you remember these things.
With a slice.
I remember Gromov, so
With a slice, not an arrow.
That's fine.
but this is so much,
We do the
this is
common category.
easy to understand.
Yeah.
This is easy to understand.
Tell the Gromov story.
But yeah, so I speak to, when I was at IHS, I spoke to Gromov pretty often, and he was extremely like, he also gets very confused about the difference between left and right. He's like, you should just have notation that indicates like directionality.
He's right.
Don't forget about the words that you're being used to describe the directionality. Just show the directionality in your notation. So hopefully this will show you it's going from the single element set to the objects of this category. Right, so these are the objects, and the morphisms are commuting triangles. So rather they're, I think of the morphism as going from x, now I draw it as x comma p, to y comma q, and this is a stochastic map from x to y that preserves the probability p to q. So actually, to even make sense of preserving the probability, I have to tell you how to compose morphisms. So I told you this is the category, and these are the morphisms, and the way that you x, y, g is, this gives you a morphism from x to, let me know if this is too small for somebody. I realize I'm trying to squeeze this back here. But it's given by taking products of probabilities of going from one event to the other, and summing all possible intermediate steps to get to the final location.
Called matrix multiplication.
It's called matrix multiplication. Exactly.
Very important.
So it's given by,
You could call it pointed fin stuff.
yeah, you could also, this has a name, I just forgot the name. Let's give it a name. Let's call it fin prob. Even though this is different from what's out there in the literature, but anyway, finite probability spaces with stochastic maps between them. So these are the so these are the objects, these are the morphisms, and this is the category that I have of interest. And there's a very interesting theorem that's associated with this category here. And I'm just going to make one other assumption about this. So I'm not exactly using this, was it slice or co-slice?
Well, let's ask Gromov.
So I'm not using exactly this slice category.
Co-slice.
Co-slice category. I'm slightly modifying it by looking at a subcategory. So this is not actually equal to, I'm going to define fin prob to be a subcategory where probabilities, and I'm talking about these probabilities,
Right.
the p's and the q's. I don't care about f, but the p's and the q's never vanish. And the only reason I'm making this assumption is because everything else I'm going to say after this is so much more technically complicated that it's not worth, it's worth taking the step from leaving the co-slice category to the subcategory rather than sticking with the co-slice category and then making every other thing have like a technical asterisk, but really technically I mean this. So I'd rather work with this and make everything a lot more precise. So there's an interesting theorem about this category fin prob, and the theorem is that there exists so by the way, this also inherits the tensor product structure from the previous category. You take the tensor product of probability distributions. So this co-slice category.
So you're only going to find the invertible maps from this subcategory.
Yeah, that's exactly.
So this is like your. I can find an inverse map if something is surjective. So this is your surjective requirement.
That's interesting.
When you say subjective, you
That's
mean
interesting.
this requirement?
No, I mean in sets, for a map.
Oh, you mean the fact that this is like a strict inclusion is really
Yeah,
nice?
yeah.
You can think of that. You can think of it like, well, I start out with the category that I have a lot of control over and I understand what the isomorphisms are. And, but I'm enlarging it and I want to know, can I extend the notion of isomorphism beyond just that subcategory? Surjections are included, like, they don't have to necessarily be surjections. Actually, because I'm requiring this condition, that these can never vanish, they will automatically be surjective in the sense that
Yeah.
every element here will be hit by at least one element with some probability. So in that sense, I'm including the surjectivity actually in this assumption.
Makes sense.
But, you know, there's a lot of good reasons, physically speaking, to also include non-vanishing probabilities, just because you can never do an infinite number of experiments to completely exclude the possibility of something happening. But that's, I don't want to go into that.
But could you just say the last sentence again? Because I wasn't able to parse it.
The previous, just this one.
Just this one, yeah.
Intuitively, if you also had a set of possible events,
Right.
and you're doing an experiment to test how likely that event is to occur, you can never really do an infinite number of experiments to
Right.
completely verify that the probability of a given event will necessarily be zero
Thanks.
in this finite setting. Okay,
That's Popper.
exactly. So the theorem says that there exists there's going to be a lot of adjectives here, so it's going to be kind of amazing. So there exists a involutive, monoidal, and what I'll call inverting functor from finprob to finprob up. So yeah, there's a lot of adjectives.
Sure.
So monoidal, I think, is fine, right? It takes the tensor product to the tensor product. Involutive, so let me give this functor a name. I'll call it B.
We call it B, okay.
I'm going to call it B for now. I should call it R for retrodiction. But I'll call it B.
Dagger, no?
Oh, that's a great point. It is a dagger. But I don't want to call it dagger because it's got this functor is due to a pretty famous person whose last name begins with B. Maybe somebody can already guess where this is going.
Jay's favorite person of all time.
So let me say what involutive means. Involutive is exactly
I don't know
this.
what the B?
Boole.
Yeah. Oh, well, this is right. What Boole published in 1854 so far, without categories.
So involutive means that B composed with B is the identity.
Right. Okay.
And inverting means B of F is F inverse if F is invertible. This is a name I made up, but I'm sure this notion exists elsewhere. So these are some of the properties. Do I need any more? I don't think so. But so this theorem says that such a function. I mean, even if you look at it, you're kind of like, wow, this is pretty special, right? It reduces to inversion on a very small subcategory of invertible functions, bijections, and it's involutive. It satisfies this. It's also monoidal. It's a functor, right? So it takes composition to composition. And
Is it the identity on objects?
oh, thank you. Yes. Fixing each object. Thank you. That's important. So it takes a probability space. That's what this XP is. And it fixes it. And the idea of it being inverting is just this notion that it takes a morphism from xp to yq, and it gives you a morphism going backwards. B of f. So that's where B of f is going. So the fact that it fixes these objects, I should have actually drawn its domain and codomain and where
This is
it's
a technical, historical question.
Yes.
Was the editor of the author B, was his name Price?
the editor?
Yeah, the editor.
The editor.
But one second, by,
I'll ask later.
by B you mean bull?
No.
By B, I don't mean bull.
No, I mean the guy before, the guy before
So-
whose work was published posthumously. And
Oh! I see. Yes,
So-
that's correct.
So who's B?
You're correct. So B is Bayes.
Ah,
Yeah.
the other B.
yeah, this is Bayes.
So
That's Bayes. I'm sorry. I'm sorry. I know you know this.
so this is what's called Bayesian inversion
That's it.
or Bayesian retrodiction or something like that. It goes by many names.
I feel bad now for not being able to guess it.
So that means that this category is gonna be something like a group or something, right? If everything is invertible in this sense? Or not?
I didn't think about what kind of structure you get when
Yeah.
you do that, but
I'll tell you what it's like.
yeah, maybe. Yeah, that's a good thing. I actually, that's a good question. Yeah, I didn't think about this.
Is that a strict monoidal?
Yeah. I mean, you know, in the in the sense like, yeah, the associator, just, right, you have
They're invertible then?
Yeah. It's strict in that sense.
Okay.
Yep. That was kind of like an infinite question.
No, but I like your, I mean.
Yeah, it's an interesting question, yeah. I think there is something to say about that.
Mm-hmm.
I mean, if you think of a Hopf algebra as a group,
Mm-hmm.
so this is, I mean, Hopf algebra is a monoid with an involutive, right, so
Yeah.
it's very interesting. And that brings in symmetries.
Yeah, exactly. Actually, that's a good, then that's symmetry, this idea of
Partial.
retrodiction, this idea of time reversal, symmetry. I mean, that's kind of related to this.
Yeah.
So let me just give the formula just in case it's not necessarily something that's familiar. But if so let me just say that if I give you one of these pairs, then what is B? So rather than writing B of F every time, I'm just going to call it like F bar for now. This is B of F. And the formula for F bar, it's got to be a stochastic map going in the other direction, so it's matrices that kind of like have the elements, you know, if it's an m by n matrix, then it's n by m. So its matrix element is given by, it's just some formula. It's a formula. But you can think of this rather intuitively. If I think of these as like water droplets as some things that are happening with some probability, and I think of, let's say this is x, this is y, and I make an observation, let's say, and I happen to initially see that my system described by the set x and probability distribution p, I see x is happening, then I can look at the joint probability of seeing x happen, letting the system evolve, and then seeing y happen. That's some probability. That probability in the forward direction is given by fyxpx. Conversely, if I noticed that I observed element y, I can deduce with what probability x occurred preceding me viewing y. And that probability is given by this f bar xy qy. And what I want to deduce is, what are those probabilities? And I can solve for that by rearranging the forms, by rearranging this formula and computing it this way. And it turns out that when you put all of these things together, you can build such a functor from this construction.
So is a functor with these properties unique? Is it the
Awesome. So, yeah. I'm not gonna, well, yeah, maybe I'll just say.
What?
It must be.
What?
Well, it's an open problem because.
Wait a second. This is an advance in the history of science.
I don't know the answer to this. I don't know the. I mean, I don't think many people have formulated. I mean, I don't think that many people know that Bayes' theorem can be formulated in such a way, and therefore, it's not clear to me if it's known whether this. So let me just state the.
As I said, a definite advance.
So it's probably a unique.
I highly think it's like
It must be.
I really think it's the only one, but
Well.
is it the unique? And I don't even know how many of these adjectives I need, but right, because like
This is great.
you know sometimes you know maybe one implies the other if you have enough, but is there unique and volutive? Let me just give this thing a name. Such a functor is called a retrodiction functor. So that's the name I'm giving to functors that satisfy this property. So the question, the open question is Bayesian inversion the unique retrodiction functor on FinProb? And I believe the answer is yes, but I have no idea how to prove it.
This is in the paper and on the archive, right? Well, everything you've done here formally is
Correct.
okay. Thanks.
Yeah, the paper is
Thanks.
the paper is written like a math paper.
Yeah, yes.
With with like interspersed physics, but it's theorems and statements and definitions are made in math style. So this is an open question, which, to the best of my knowledge, is formulated for the first time in this paper, because the definition of this, like the definition of this type of a functor, was given there. That's why it's an open question. That's why it's fresh. You know, in particular, like how do you get this like inverting procedure to happen from just these axioms? I don't know. Or if you need other axioms. If you find another one, that would be interesting too.
That'd be very interesting.
Exactly. So, okay. Wow, this is great. I actually didn't expect to get through that whole part this quickly. So I can start the quantum side. So is this part okay so far? Because I was, I'm not being precise about everything. That's what the paper's for, but hopefully I'm saying enough that you follow. And if not, then please ask. Okay. Right. So in quantum, there's a big difference in quantum though. And one of the big differences is that in general, it's not even known what it means to do retrodiction. Like how would one even describe it? For example, in quantum mechanics, if you prepare a system and you make a measurement, then you're probing the system and necessarily changing the system as a result. And when you do that, the notion of retrodiction is a little bit, it could be a little bit confusing. How can you retrodict about the past and test something about the past if you've already changed the experiment as a result of your measurement? There becomes a little bit of a philosophical issue, and I don't think it's really clear how to do that. So I'm not going to address that problem at all. Instead, I'm going to use this reformulation of Bayes' theorem as a guide to defining actually what we mean by retrodiction in the quantum setting. So in quantum, FinProb gets replaced by a category of non-commutative probability spaces, and the quantum version and quantum analogs of what are called noisy channels. So what exactly do I mean by that?
Or better question, I mean, where did you see commutativity any place beforehand?
I think you'll see it when I'm about to give how this is generalized, and then I'll do the example of the commutativity.
Okay.
I think this idea of doing things this way has a long history. I think dating at least to the 30s or 40s, maybe Josiah might know. Dating back to like work of Gelfand, Neimark, Siegel, just about how one thinks about non-commutative probability and what that means. I'm sure that there are other approaches, but the one that is lurking in my mind is the one that I'm about to say. So these pairs, xp, I shouldn't draw an arrow, gets replaced by A, which is some kind of an algebra. I don't want to be too technical, so let me say it's a star algebra. So it's an algebra set as a product, it's a vector space, they're compatible. It has a notion of a star, which is like it's an involutive action, and what I'm going to call a density operator, or maybe I'll just call it a state. That's probably better. And a state is sort of like a I don't know how to say it other than using words, a non-commutative version of a probability. So maybe it's good to give an example. So let's take A to be Cx. So these are functions, complex valued functions from x to the complex numbers. That's an algebra. The algebra functions on a finite set. And alpha, I'll tell you what a state is by writing out what it means in this case. Alpha in this case is going to be some function, but it's going to also satisfy the property that alpha equals beta star beta for some function beta. Beta is not a good letter. A star A for some A and A, and the sum or the trace of each of the values of the function in each element. So and trace of alpha, which is equal to the sum x alpha x equals 1. So this condition, this star here is just the complex conjugate. So you have a complex valued function. You take the complex conjugate of each value, and then you multiply it. In other words, if this is a function whose entries are all non-negative. That's the first condition. And the second condition is the sum of those entries equals 1. So that's exactly what a probability distribution is. But this more general idea of a state inside of a star algebra says, I have some algebra, some star algebra, and that element is the product of some other element with its complex conjugate. And its trace, so this star algebra also has a notion of a trace, is equal to 1.
Let me just ask a technical question.
Sure.
So you wrote A is maps from a finite set X, just a regular finite set, or
Yes.
not?
Yes,
Okay.
X is always a
And
finite
then
set.
star, so you imagine you give an ordering to it, and then you get a column vector of complex
Yes,
numbers,
if I
and then,
think- yes.
let me just say it, just because I'm not too
Good.
clear on all this. So you transpose it, but you also take the complex conjugate of each of the elements, right?
Yeah, you don't transpose it. So
You don't transpose
yeah.
it.
So alpha is like an alpha x1, alpha x2.
Right,
And in this case, A star A
right.
is
What's
like, I know it's going to look funny, it's like
Right.
A1 up to A, I don't know, M.
that? Yeah,
Star, in this case, is just the complex conjugate of each entry. No transpose here.
I feel better.
You feel
Oh,
better.
no, wait, I'm sorry. Go ahead.
I think you might feel worse.
No, I feel worse.
And the product of these two things is the point-wise product. The way we take the product of two functions is, right, f of x times g of x,
Right.
sorry, f times g of x equals f of x times g of x. That's what you do here.
Take the point-wise from
I think I know which example you're thinking of, and that's the non-commutative one, which I'll do next.
Many,
I'm sorry, okay.
many of my students
I feel a
multiply
little better.
matrices like this.
So yeah,
I feel
so
a
I'm
little
not multiplying vectors. I mean, I am multiplying vectors, but I'm multiplying them by thinking of them as functions,
Right.
and then that's a little bit more
So
natural.
what
Okay, so this is the commutative case.
This is the commutative case,
This is the commutative
which
case.
reduces to fin
Under
product.
enough definitions.
Yes.
Gotcha, thanks. I was just misunderstanding.
And the trace part is Born rule?
And the trace part is just the, what is it called? The fact that a probability distribution sums to 1.
What's the
It's, yeah, it's a little tech, yeah, I'd have to talk about something else to talk about
What's the
Born rule.
Born rule?
I can talk about the Born
No,
rule.
don't talk
No,
about it.
You're doing
You're doing
excellently as far as
perfectly.
I'm concerned.
Okay.
Don't talk about the Born.
World class.
I mean, so yeah, there are some things I didn't define, like what kind of a star algebra?
Yeah.
I don't want to do
We
that.
all know what a star algebra is, for goodness.
Yeah, technically it's like I'm working with what are called finite dimensional C-star algebras, but I don't want to do that today.
What about the factors? I'm sorry.
Yeah,
Sorry.
That's
sorry,
exactly-
Sorry.
so let me give this non-commutative example. And then you'll see where this transpose can appear depending on the algebra, and that's when it's a non-commutative algebra. So a nice one, for example, is let's take A to be 2 by 2 matrices, and alpha to be the matrix well, okay, I'm going to do a bad one now. But it's this matrix. And, oh, should I have done this one? Yeah, I think I can do this one. Notice that alpha equals, oh, and so here what is alpha? A star, if A is A11, A12, A21, A22, then A star is, this is the complex, this is the, what is it called, transpose conjugate transpose? And in this case, alpha satisfies these conditions. Its trace is 1, so trace is 1. Trace means the sum of the diagonal entries. And it also equals A star A, where A equals 1 over the square root of 2. I hope I did this right. Did I do this right? No. It's this. So if you take the, in fact actually alpha equals alpha squared. So in this case, alpha satisfies these conditions, and alpha corresponds to a state in quantum mechanics that you can describe as being a mixture of spin up and spin down. Anyway, you can construct such states in the lab, or you can construct states in a lab that are modeled by this matrix algebra together with this particular matrix on this particular state. Okay, so these are what the objects look like. They can become more complicated, and they describe a lot of what they were used to describe the mathematics of quantum mechanics. And if I were just as in the setting of finite sets and functions, the isomorphisms there corresponded to bijections. In the setting of algebras, the thing that corresponds to bijections are called star isomorphisms. They preserve the algebra structure, they preserve the sums, they preserve the products, they preserve the scalar multiplication. and they're invertible bijections. And what are noisy channels? So what is a noisy channel from one algebra to another? These are things that do the following. They take elements of the form, of this form. So this is a matrix whose, it turns out that in the case of matrix algebras, this corresponds to a matrix that's self-adjoint and has non-negative eigenvalues. And they always give you something that's also a matrix that is self-adjoint and has non-negative eigenvalues. So these are what are my noisy channels. And there's another, this is called a positive map. And they also satisfy another condition, which is that the trace, so I can define a notion of trace just like for matrices on these kinds of algebras, finite dimensional algebras. And I can define a trace that satisfies the condition that if I compute the trace first, or I can apply this noisy channel first and then compute the trace, and I get the same thing. Then these form what are called noisy channels in the setting of quantum mechanics. And there's actually an asterisk here for this. This is a different kind of an asterisk. But technically, I don't really need to work with positive maps in the setting of quantum mechanics in order to get a monoidal structure on this category. Actually, this is where it's said, because I'm going to say it in a way that's not described by physicists. So technically, we need what are called, in the literature, they're called, if you've ever seen this before, they're called completely positive maps.
Yeah.
It's another condition, and physicists usually describe it by saying, you take the tensor product with some matrix algebra with an identity, and you want that to be positive, and it just seems kind of like, where is this coming from, like as a physicist? As a mathematician, complete positivity, this guarantees a monoidal structure. A monoidal, a tensor product on your category. So if you just took one of these things that are called positive maps, then you wouldn't be able to take their tensor product and get what's called a positive map in general. But you can modify that a little bit slightly and get something. So actually, let me say where these conditions come from in the first place. By looking at the two examples we have, I don't know if I want to do this.
Can I ask a question?
Yes.
Originally, like for Finstock, it's like the Kleisli category for a probability monad.
Yeah,
Are there
yeah.
anything going on? It doesn't look like this is.
It doesn't look like it is, but there's a paper by Westerbaum. This is a side remark. There's a paper by Westerbaum that actually does say that you can do this as the Kleisli category of some monad, but I think I spelled that correctly.
Okay.
I can't remember if it's Westerbaum and Westerbaum, they're twin brothers, but at least one of the Westerbaums is on it, and gosh, I think if you search the word like Kleisli category quantum channels, you'll find the paper. But that paper does construct the category of completely positive maps as the Kleisli category of some monad.
On like just star algebras?
On certain C-star algebras and star homomorphisms, which are kind of like correspond to functions, but it's not constructible. Like you don't know what it is, like what it's doing.
They just show it exists?
Yeah, they just show it exists, and they computed it for like very, very low dimensional examples, like
Interesting.
1 or 2 and 3
That
dimensions.
is certainly interesting.
But as far as I'm aware, nobody knows what it actually is concretely. So I think that's an open question still too.
That's great.
So
That's just utterly great.
yeah, there's a lot of interesting stuff here that's just totally open, and you don't really need to know that much to get to those open
Yeah,
questions.
it's just the beginning of the whole subject.
So let me just say the motivation for these two axioms comes from exactly the idea of a stochastic map. If I restrict my algebras to be function spaces and my channels correspond to these things called positive maps that preserve the trace, preserve the sum of the entries, then I recover exactly a stochastic map. I can show that there's an equivalence of categories between thin stock and the subcategory of this of algebras and positive trace preserving maps when I restrict to the commutative ones. There's an equivalence between of categories, and therefore stochastic maps correspond to positive maps, and therefore you get a feel for why this is potentially a good definition, but it cuts short because if you wanted to get that tensor structure as well, then you need to consider completely positive maps on your whole category, which is just an extra technicality.
But please, this is embarrassing for me. What do you mean when you say you restrict to the commutative? What's commutative exactly?
So the algebra structure on this star algebra. So in the case of matrices, that is not commutative because there exist matrices A and B,
Right.
for which A times B does not equal B times A.
Right.
But for algebras of this form, functions,
Right.
if I take an ordinary function f times g,
Right.
then that's the same thing as g times f. So
Absolutely.
when I say restrict to a subcategory of commutative algebras, I mean
Ah,
restrict to the objects that are commutative C star algebras.
understood. Thank you.
And
Thanks.
And then all the morphisms
There's
between.
another way of interpreting it, and yeah, I won't go on.
Okay.
Yeah, sorry. You work it. I'm sorry.
No,
Okay,
it's
understood.
either way.
Understood. Okay.
So that gives like a slight motivation for that axiom. And then maybe I'll just say, did I finish? No, I didn't finish, but it's the same story. So I talked about like xp gets replaced by x alpha. So you construct a slice category, right, where you're now it's the slice category. Sorry, this is still co-slice. This is still co-slice. You construct the co-slice category, the thing that replaces the single element set is the complex numbers. And then you do the same exact construction, and then again the same thing where I said, but you want to be careful, you want to get rid of things with probability 0. So then you just need to make sure that your probabilities or equivalent of these matrices have no 0 eigenvalues. This is an example of a matrix with a 0 eigenvalue. So we don't include these in our category.
In your category.
So let me say that there's a category called, I forgot the name. We give it a name in the paper, states. I don't know, states. And this is a category whose objects are pairs A alpha, where same as here, alpha is a state, but alpha has no vanishing, I'm going to say quote-unquote eigenvalues.
Yeah.
Because, yeah.
Sorry, so there are things that you can make in the lab that you don't want to include in your category. Is that a problem? Or
It's the same kind of problem. Well, it's actually not exactly the same, but it's kind of the same problem as, right, in statistics, you can't do the measurement. You would have to have done the measurement.
I see. So you can perturb this arbitrarily
Exactly.
small amount. And,
But unfortunately in the quantum setting, that perturbation, the discussion of that perturbation is non-trivial, unfortunately.
Okay.
Yeah, it's a little bit more subtle. I thought about that for like 2 years, and the answer is not as easy as it is in the case of commutative probability theory, unfortunately. But But again, even if I included it, you could make sense of a lot of these axioms, but they just become more technical. Yeah.
But in the case of the commutative thing, there's the bizarre definition of conditionalization, which when you're an undergraduate and you see it, and you say, "Whoa, what the hell is that?" Is that what you're talking about?
Yeah, so actually,
Okay.
if you, conditionalization occurs like for special morphisms.
Right,
Maybe one of them corresponds to a function,
right, okay.
and then like the conditioning is just, one of them is a function, the other is a stochastic map.
Right. In the case of the commutative thing,
Yes.
it only comes up in the case of infinite, dimensional things. Because for finite things, it's.
Oh, I see what you mean.
In other words, there's this bizarre definition where you need a sub-sigma algebra.
Yes.
And that takes care of the approach to zero.
I see.
But that's all.
So, I see.
Okay,
Yeah.
I'm sorry.
So
Sorry.
if you were to, I don't know what happens when you think about infinite dimensional stuff, because again,
Right.
I was more interested in generalizing
Right,
quantum setting
understood,
rather
understood,
than
understood.
the measure theory setting.
But it's striking.
Yeah.
Like, what the hell are you doing?
So I think there are ways to discuss what I'm talking about
Right.
in an infinite dimensional setting as well.
Right, right.
But
Okay, no,
I won't-
sorry.
I won't do that.
Yeah.
No worries.
Yeah.
Right. So these are what the objects are of this category states, and the morphisms are these noisy channels, just as in the usual co-slice construction, such that like the appropriate diagram commutes. And by these assumptions about complete positivity and stuff like that, this forms a monoidal category as well. So you get all of these nice structures, just as you would in the setting of finite probability spaces. And then there's a theorem. You can see the thing. I was like halfway through my talk, I was like, oh, this is good. I'll be able to do the same thing for quantum mechanics. It's exactly like the same exact talk twice. There exists, I wish I remembered the way I said, the order in which I said this. There exists a involutive, monoidal, inverting, functor from states, fixing every object. Is there a word for that? I mean, dagger, there's a dagger
Yeah.
on this.
It's a dagger
Yeah.
structure, right?
States,
Plus one.
the states up. This time I'll call it R. R for retrodiction. So first of all, there exists such a functor like this. And the same properties I wrote before, right? Like, takes the tensor product to the, oh, no, well, I'll have to,
It's very similar to the problem of, it's similar to the problem of
It's on the
retrodiction,
video.
except
Yeah.
you'll have to do the
It's-
Bayesian reconstruction here.
yeah, basically the question
But
is,
without past, actually,
the question is
you are
like,
retrodicting the past.
yeah,
Let him
so the
finish.
question is what takes place of that Bayesian inversion? I realized I'm one board permuted over, that's why this happened, right? Because the theorem was there. The way that this guy is constructed is that if you give me such a map here, then R, I'll call it R of E, maybe I'll just use the usual notation, right? R of E is going to be something that goes from B to A now. And what is it? Unfortunately, there will be now two parentheses. This isn't the notation I used in the paper, but R of E applied to some B is given by the square root of alpha 1 over the square root of beta. It's not an obvious formula. So it's given by this formula where this star here I'll call it an adjoint. So these star algebras, I'm in the setting of finite dimensional algebras, where these algebras also have a natural inner product. And this is an adjoint with respect to that inner product. They also form Hilbert spaces. This is an adjoint in the Hilbert space sense. So it's given by this formula. And in the special, so this is, this is where the proof ends. You just have to show that this thing actually satisfies all of these properties, which takes time, but you can do it. Mm-hmm.
Maybe you want to call it MP instead of R. I'm sorry, I'll tell you later.
Do you know why?
Yeah, more Penrose.
Oh, I see.
I'm sorry.
So people do call this P, but this map, this map here, is due to, as far as I'm aware, somebody called Pets.
Okay.
I don't think the name would be familiar with.
It may be a completely different formula.
I see. And in the special case where these algebras are commutative, it also reduces to Bayes' rule. So when these algebras are actually commutative, then these matrices commute.
Understood.
And this beta is like your Q. Maybe I'll write the formula here, just to remind you where this, like, why you sort of see this happening.
Yeah.
It's kind of like square root of px, square root of px, and then you divide by. Well, I kind of did this in a weird order, right? But you have like square root of qy here and square root of qy. That's kind of what's going on here. The p's are replacing the alphas, the betas with the q's, and this E star is like taking your stochastic matrix F and reusing it. The star is just there, but you have to use it in the other direction. It's kind of like viewing the stochastic matrix as it's a transpose. But the point is, you have such a functor, and the same open question is there. Is it unique? Meaning, is it the unique retrodiction functor? On this larger category now of not just commutative spaces, standard probability spaces where you reduce to Bayesian inversion, this is a slightly more ambitious question. Same properties, but is it the unique retrodiction functor on this larger setting of matrix algebras and what are called states? And although we don't answer this question, we do something. So in this paper that I mentioned at the beginning, we do give a lot of evidence for it. And the reason we give a lot of evidence for it, unfortunately, I can't go into details for all of this, but there are many candidates for retrodiction in the quantum literature. So if you look at the literature, we give essentially a table of many examples of things that people could view potentially as retrodiction, things that were maybe not necessarily explicitly proposed as retrodiction, but some idea of this kind of notion of trying to invert a channel to the best of one's ability. Many people gave proposals for such a thing, and we checked many of those proposals and found that they all every single one of them fails at least one of these axioms.
Wow. Okay.
And the only one that seems to hold is this one, again suggesting the possibility that this may be the unique one, but we don't know because it's still an open question. So I think this is a big open question for, these are two big open questions, both in the setting of classical probability theory. Is Bayesian inversion the only notion of retrodiction we can have that's compatible with these very natural categorical axioms? And then you can also ask the more ambitious question is, in quantum mechanics, where this question is, in some sense, this is the first, it's kind of like wide open. In some sense, this is kind of like the first mathematical question about retrodiction that one can make precisely, which is this the only retrodiction functor which has a precise notion that exists in quantum mechanics or not? And if there are alternatives, what are they? And how can they be used? I also didn't go into how these can be actually used. I just talked about their mathematical properties. But there are a lot of interesting questions that you can ask about how to use such maps, for instance, in quantum computers, or there are aspects just like you would normally use inference to try to deduce something about the past. But it's very interesting to understand what other possibilities are there with respect to this model definition for what retrodiction could mean. So I think that's kind of a nice place to end the talk at like an open question for this field. So thank you.
Any questions? Any discussion?
Yeah, so I have a definition of non-commutative probability space that it's an algebra together with a linear functional, an expectation map. So it looks to me like there might be more than one choice for a reasonable linear function. Maybe you could inner product with the state, or maybe you take the trace of an element of the algebra times the state. So what is the analog of the expectation in this case?
Good question. So the version that you're thinking of is necessarily more general because your algebras don't even need to have a trace.
Right.
The things that I'm talking about form a subclass of that, where you do have a trace, and then the expectation value is given by exactly what you just said, trace alpha of whatever element you have.
Okay.
Do you want me to write the formula?
No, I understand. Trace of alpha times the element.
Exactly. That's your functional.
Mm-hmm.
And there's a theorem that says, in this case too, if you give me such a functional, then there exists a unique alpha for which that functional equals trace alpha blank. But in the infinite dimensional setting, we typically work with the functionals because you might not have a representative element alpha.
Mm-hmm. Right.
I'll be honest with you, the only reason I formulated it this way is because typically the quantum information community works by using those representatives rather than by using the functional perspective, which it's just depending on your audience. I kind of wanted to gear this work to the quantum audience rather than the... Anyway. But yeah, once you see that, you're like, okay, I understand. Once you relate one thing from one language to another, then yeah, this also has a name in computer science, right? States versus effects, I think.
What is the effects?
Is that what I'm talking
I
about?
have no idea.
Yeah, okay, I don't know, because I don't do computer science, but I know that...
Do you
so
mean effect as in the Pascal's effect monad?
Oh, I don't...
Well, why don't you just say what you mean by effects here?
Just essentially what I said to Josiah, but using what I heard computer scientists use different words. Like rather than representing functionals, you can represent the elements representing those functionals in terms of... I'm not sure. Anyway. Or maybe they're called predicate? No, I don't know. Let me retract my statement, but I think there's some stack exchange that says computer scientists, what physicists call the Schrodinger and Heisenberg picture, computer scientists also give it a name. And I unfortunately forgot the name. I think it's something to do with states effects.
I wouldn't use Stack Overflow. I'd use GPT-5. And it can always be trusted because the editors, they're so careful and.
I see. Okay.
Okay.
Yeah.
Yeah, so I know that there's been a lot of work on like Bayesian inversion for like Markov categories and stuff like that. How did all those different like notions compare with like this kind of simple definition you gave?
That's a good question, and I don't know the answer. So, as far as I'm aware, yeah, no, I do know the answer. This definition is more general because if you extend the definition of Bayesian inversion in the Markov category setting to the quantum setting, it turns out no such functor exists. Because the condition is a little too restricted. What you do have, however, is there exists a subcategory for which Bayesian inversion exists.
But it's not a Markov
But
category?
it's not a Markov category in the usual sense, no, because your copy morphism isn't a morphism in the category. You have to enlarge your category to include a copy morphism. These are called quantum Markov categories, which I have a paper on. And I described how to extend Markov categories to the quantum setting. But that's not the end of the story. I think there are other people who think there are other ways to include quantum systems as well.
It seems then that the definition is kind of wrong, right?
I don't know. I don't
Like
want to say
if like
it's a
this doesn't
definition.
work for like quantum Markov category, it's like
Sorry, no, this word. Oh, sorry.
Like-
So, what I mean to say is that if you use the definition, there's a definition of what a Bayesian inverse is for Markov categories involving an equation of string diagrams, essentially. If you use that same definition and you try to include non-commutative algebras and probabilities, then you can show that there does not exist such a functor, which means that that condition is too strong. The definition from the setting of Markov categories is too stringent of a condition to generalize in a robust manner to the setting of quantum systems. So I actually have a paper on that exact question. And this is more recent work. This is where we found a way around that no-go theorem by weakening what we mean by retrodiction or Bayesian inversion by using this functorial perspective instead.
I mean, could it be that like, you know, you have just a different, you know, because they normally do, as you said, like the equation of string diagrams.
Yep.
Could it be that like, if you change somehow that definition in the quantum setting, you get this?
I don't know how to do it, and the reason has to do with these square roots. So even if you try to use like the string diagram calculus of like Bob Koch's quantum mechanics in that school, Bromsky school, that version, then the square roots are inside of there, but they're working with something that's larger than a Markov category.
Is it stupid to ask what a Markov category is? Can it be said in 2 sentences or not? No.
It's a
It's
It's a monoidal category with a... I think I can say it nicely, but I'd have to think for a moment.
Okay.
Yeah.
Sorry.
Yeah. Gershon.
Just on the dagger thing, because I just want to be clear, because, you know, Nost observed when you mentioned again that what you're describing as a retrodiction functor looks a heck of a lot like a dagger.
It is, I mean, yes.
Is it literally, is it dagger plus monoidal, or does monoidal imply by dagger?
So technically dagger means this involutive part and the functor part, and fixing every object part.
Right.
So underline means dagger.
Okay.
And then you can ask for a monoidal dagger functor.
Yeah.
That's when you include this. Inverting is something I don't know if that's something that's normally considered in dagger functor literature. Where, right, because a dagger functor goes from a category to itself, it reverses the directionality of morphisms. Maybe, I'm sure that there exists somebody who's thought about, oh, I want inverses to go to inverses too. And maybe they gave that a name. If you know that, please let me know. But
Something like unitary.
Yeah, I was going to say, unitary or self-adjoint are the two
Unitary?
conditions people put on. Might be one of those, yeah.
I see. Well, then maybe it's good that I use the word inverting, because I don't want to use the word unitary in the setting of quantum information theory, because that would confuse everybody. But I'm sure that the word exists.
Okay, so that's what I wanted to understand. So this is very close, and it's mainly the monoidal thing and then sort of this other condition.
Yeah. But again, I don't know how many of these conditions are actually necessary. Maybe some of them imply the others in this category. Like if you restrict to this category and you try to like say, oh, I want an involutive unitary functor fixing every object, and I just drop this part, is that unique? Because actually, also in our examples, if we required that, we also didn't find a counterexample. So is the monoidality a consequence in this setting of the other axioms? I don't know.
That would be a good guess, I think. I think, if any of them, just shooting from the hip, that the monoidal would be the, yeah.
There are intuitions coming from quantum information theory why this one could be viewed as a sort of a consequence in some sense. You can get it from composition.
Okay.
In certain cases, yeah.
Can I, rather than ask a question, can I play a word association game?
Yeah,
I
please.
say one word and you talk about it.
Okay.
It's not good. Ready? Determinism.
Star homomorphism.
Okay, quantum eraser experiment, delayed choice quantum eraser experiment. I mean, you're brushing up against these topics.
Yes.
You're not...
Yes. This is a topic of a different area of my research, which is also closely related to this.
Okay.
Let me say.
You have to make one sentence and then we'll finish. You don't even have to. It doesn't even have to be a coherent sentence. It could just be a word.
A non-commutative version of joint probability has something to do with a non-commutative version of joint probability. It's like eraser experiment is sort of like entanglement in time, right? Kind of causality-related notions. And causality-related notions in quantum mechanics, actually something interesting happens. Bayes' rule, I actually wrote it in two different ways earlier. I wrote it as a joint probability equals another joint probability. And a priori, if I had no axioms in probability, but if I had zero assumptions on axioms, those two things don't have to be equal to each other. And there's also the other version, which is like, oh, I can view the constituent parts, this fyx, the f bar yx, is happening in time, from one time step to another, and then I can define Bayes' rule using that notion. That's the perspective I took in this talk. View Bayes' rule as coming from processes and directional in time. There's another version where you can try to construct joint probabilities coming from different directions, and then comparing the two. And in the setting of quantum mechanics, those two perspectives about Bayes' rule lead to potentially different results.
Yeah.
And so, in this sense, Bayes' rule in the setting of quantum mechanics distinguishes, in some sense, between correlations that happen in space at a fixed time versus correlations that could happen temporally in time. And as a result, you have Bayes' rules that correspond to different aspects of those situations. So that was a very long explanation for something like this.
We'll watch it again on the video.
But I have other work that goes in that direction too.
Love to see it. Anyways, I think we should thank the speaker.
Thank you.
I really liked all the questions.
Thank you all for coming. Please come again. Next semester we're going to have more in-person talks. Are you going to give in-person or on Zoom?
In person.
Perfect. Anyways, looking forward to seeing you all. Thank you.
Thank you.
Arthur, thank you.